we are really getting towards the end of the semester. And you know, sometimes at Marshall we have 2 weeks after Thanksgiving until the semester's over, and sometimes we have 1 week, and this is a year where we've got 2 weeks. I kind of prefer it the other way, you know, like I like to go into Thanksgiving knowing that basically we're out of here, but we're getting close, but we're not fully out of here yet. You've got 2 more homework assignments. You've got homework 7A and 7B. And homework 7A, I forgot to put when that's due. Anybody have the, let's see, the schedule says that's due on Thursday, December 1st. So let me put that here. You've got some time on that one. Due Thursday, December 1st. All right. Chapter 7 is really important because it directly leads to where we're headed in hydraulic engineering next semester. So far we've talked about the forces that act on a fluid, like pressure as we go downward through a static fluid, or gravitational forces, or the effects of shear stress. So those are the mechanical forces, and when we start to account for energy, then we can solve a lot more problems. You know, till now we've kind of had some unrealistic assumptions when we've applied Bernoulli's equation, for example. And we want to liberate ourselves from those unrealistic expectations because we've been confining ourselves to points that are very close together in order to predict differences in pressure between the points. But most water networks occur over miles and miles, and so we have to be able to predict pressure changes over more lengthy distances than Bernoulli's equation alone could handle. So in the energy equation, what we're going to be doing is looking at losses of energy, no longer assuming that no energy is lost as water flows from one point to another. I mean, you saw it in the lab when you worked with the Venturi. You saw that the energy grade line wasn't flat. It went downhill. It was pretty flat, but we were talking about a section of pipe that was a foot. And so you saw physically with your eyes, due to the piezometer tubes that were coming out of that Venturi, that on the upstream end there was more energy than on the downstream end. And so we need to consider energy losses. And when we do that, we can calculate how much power is required to move fluids from place to place. We can consider the effects of pipe friction, which we've known about since almost the first day when we talked about the velocity profile in a pipe, that the velocity at the center of the pipe is faster than the zero velocity at the edge of the pipe. So we've known about this force for a really long time, but yet haven't done anything to try calculating its effects quite yet. We can find out how quickly water will flow from one tank to another, because that's governed by energy losses. And we have an example we'll work through today that illustrates that. And also there are, in addition to pipe friction, there are energy losses due to flow through fittings, bends, and when you've seen the pipe rack in the lab over in the other building, you notice there's all sorts of little gadgets on that pipe rack, like different types of angles, different types of valves and fittings, and the purpose of that pipe rack and all the equipment that's bolted onto it is so that you can get experience measuring physically the energy that's lost due to those obstacles. So all of these things are important. Now, this is what you've seen so far, is Bernoulli's equation. Bernoulli's equation, remember, had a couple of key assumptions. Who can rehearse what are those assumptions that we kind of had in the back of our mind when we were applying Bernoulli's equation? Inviscid fluid, meaning what? It has no viscosity. No viscosity. So in other words, there's some magical fluid out there that because it has no viscosity, it's okay for us to put it into that equation because that equation isn't accounting for energy loss. And the only fluid that's going to be okay with that, that's actually going to behave in the way we expect, is some fluid that has no viscosity. Because fluids that do have viscosity are going to experience energy loss because they will be delayed at the edge of the pipe, and at the center of the pipe they'll be flowing more freely. But this mystical inviscid fluid would be able to just flow through a pipe without any shear stress resistance whatsoever. So, right. The first assumption is inviscid. What's the other? Incompressible. All right, so incompressible is still going to be an assumption that we use in energy equation. But like Bernoulli's equation, energy equation can be used for both liquids and gases. So that's number 2. We've done inviscid, incompressible. What else? Along the same streamline. And so in Bernoulli's equation, we weren't necessarily using the average velocity in a cross-section of a flow, but rather we focused on velocity at a certain point. And then the last assumption had to do with steady flow, meaning that conditions aren't changing over time. So those were the 4 pieces of information that we used in the past for Bernoulli's equation. Now, in the energy equation, it looks very similar. There are a couple of new terms. I know why. It's because of the podium, right? I was thinking that the screen looks even worse than usual, but it's because this podium isn't against the glass. I think you'll be able to see a little bit better when I do this. Well, not a lot. Okay. The pressure head term is the same. Each term in the energy equation is going to have what units? No. Meters. Why meters? Well, we know that Z has meters, right? If we're going to add these together, then every term has to have meters. So that's the easiest way to know that it's meters, is that elevation is meters. But then if you look at all the rest of these, it works out to meters as well. So pressure is newtons per meter squared. Unit weight is newtons per meter cubed. And so that extra meters in the denominator pops up to the numerator. Everything else cancels out. So each term here has units of meters. So pressure head is the same. Velocity head has 2 differences compared to what we were doing before. Previously, in Bernoulli's equation, remember that we were applying the velocity head at a specific point. Now, this V bar is saying the average velocity in the pipe. So it's not along a streamline that we're applying the energy equation. It's from average cross-section to average cross-section. This other term, alpha, is called the kinetic energy correction factor. And I'll tell you about that in just a moment. So there's our velocity head term. Elevation head is the same. Now H sub P is referring to the energy that's added by a pump between 2 points. And by the way, there's something else that's new in, do you have a marker for me? I thought you might. There's something else that's new between the 2 points, and that is, in Bernoulli's equation, it didn't matter if one was upstream or downstream. You know, 1 and 2 were kind of interchangeable because both sides of the equation have the same thing. But now in the energy equation, there's different stuff on the left side compared to the right side. So you'll notice here is saying HP. Over here it says HT, which means turbine. And then there's also this other term, H sub L, which is head loss. And so now there's an important directional component. And what we assume for the energy equation is that water is flowing from 1 towards 2. All you have to do to get water to flow from one point to another is just to write 1 upstream and 2 downstream. And that's the magical power that makes water flow. Okay? Not really, but that is the convention that we'll use, is that 1 is upstream, meaning that that's where the water's coming from, and 2 is downstream, meaning that that's where the water is going to. All right. So the reason why I bring that up is, let's say that between 1 and 2 there is a pump. Here's the symbol for a pump. It's a trapezoid on top of a circle. Okay? That means that there's something here with wires going to it, and the pump is adding energy, and so it's increasing the pressure of the flow, and it's on the left side of the equation, meaning that what this all adds up to is that the energy at 1 plus the amount of energy added by the pump is equal to the energy at 2 plus how much is taken out in the system from the turbine and how much energy is lost through pipe friction and local losses. So when I say energy at 1, I'm talking about the 3 terms of the energy equation: the pressure head, the elevation head, and the velocity head. Because those are the 3 places that energy can be. Those are the only 3 places that energy can be in the pipeline. They can be potential energy, which we usually think of as pressure or elevation, or it can be kinetic energy, which is the velocity head. So we're saying that here at 1, there's just a certain amount of energy related to how quickly the water is moving, velocity, related to its elevation above some datum, and the amount of pressure that's in the water. So if we're going to do this accounting procedure of trying to find out how much energy is there at 2, well, the water is flowing along and it encounters a pump. And so the energy at 1 plus some new energy. So that's why the pump head term is on the left side of that equation, is because we're adding the amount of energy that's added by the pump to the amount of energy that was at point 1 as the water's flowing towards 2. But as it flows towards 2, the amount of energy that remains once it gets there to location 2 is reduced by 2 things. If there's a turbine extracting energy, a turbine generates electricity, or if there are losses, meaning the energy losses due to pipe friction and so on. So it really accounts for everything we need it to. So here's the energy equation. Let's look again at the terms. V bar is the average velocity in the pipe, and we can calculate that. V bar you get from Q divided by the area. You can sometimes do a physical measurement of the velocity. There are magnet meters that wrap around a pipe and kind of sense the mass that's flowing through at a given time. And if they know the temperature of the water, they can turn that into a volumetric flow rate. And if you put in the diameter of the pipe, then it'll turn into a velocity. Those meters are expensive. They're several $1,000s each to know what's the velocity of flow through a pipe. H sub P is head supplied by a pump. And it's important to focus on supplied by. That means that the pump is giving energy to the system. H sub T is saying head given up to a turbine. And again, instead of supplied by, which means energy coming in, given up to implies that there's energy leaving the system because of the turbine. So energy is being lost there. And that's why it's on the right side of the equation. We don't have to put in a negative sign because energy is leaving. All we have to do is say if it's on the right side of the equation, then it automatically will be subtracting from how much energy is left over at 2. Because if there's lots of energy that went into the turbine, then there will be less left over to go into P2, V2, and the elevation head. That's a good question. That's a good question. Only in the most extreme circumstances of really high velocity. Otherwise, there's very little heat of the fluid. So water flowing through a pipe, generally the increase in temperature because of turbulence and pipe friction is not measurable. But there are circumstances where you can, if you have velocities usually in excess of what the pipe could withstand over the long term before being scoured. So like the type of velocity you'd need going through a pipe to heat up the water would cause a pretty rapid breakdown of the pipe before you saw a significant increase in the water temperature. H sub L stands for head loss, and it has 2 components. H naught, which is the local losses, and H sub F, which is frictional. So don't confuse H sub L to think that it means local losses. It's just one of those unfortunate things that L makes people think sometimes of local instead of just losses. head loss overall has there two ways that energy can be lost as the flow goes from one place to another. And then finally the kinetic energy correction factor, which I'm going to tell you about right now unless there are any other questions. Okay, so you remember that there is a typical velocity profile for laminar flow that looks like the shape of a bullet, this parabolic shape, where the velocity at the center is the maximum velocity, and then the velocity is decreasing as we get closer to the edge of the pipe because of the influence of pipe friction. Well, when we are using the energy equation over here, if we use just the average velocity, which is what V bar means, we're trying to say where is all of the energy in the system. If you just use the average velocity, then you actually would be undercounting how much energy is in the system as velocity head. Because of this shape, the average velocity would just be, if you think of this graphically, the line that half of the area under the curve is to the right, half of the area under the curve is to the left. But we are going to be squaring the velocity, and so if we integrated rather than just taking the average velocity, it turns out that using the average velocity sort of undercounts how much energy is in the center of the pipe as the kinetic energy. In other words, in the center of the pipe, the water is moving really fast, and just using the average velocity doesn't account for that. It underrepresents the actual effect of velocity head. And so we can go through and find that under laminar conditions, when we have this nice parabolic shape, that the kinetic energy correction factor is actually 2. And so what that means is, if you have laminar flow, there's twice as much velocity head in the system as you'd actually expect by just using the average velocity. So we have to multiply the velocity head by 2 to find the actual amount of energy that's there in the velocity head. But it's very uncommon to have laminar flow. You saw in the lab when we were working with the Osborne-Reynolds apparatus that injecting the dye, that we had to really crank the flow rate down extremely low to encounter laminar conditions. And so it's far more common to have turbulent flow. And the kinetic energy correction factor that you should use for turbulent flow is 1.05. And 1.05 is close enough to 1 that in many cases people just say, let's ignore the kinetic energy correction factor. So unless, like in a problem statement, unless it goes to the point of emphasizing that you should account for kinetic energy correction factor, it's okay for you to just use alpha as 1. But I did want to tell you that the full-blown accurate energy equation has that correction factor on it and what it's related to. It's related to the velocity profile. Any questions about that? All right. So let's use the energy equation. We have water flowing from one tank to another, and assume that the tanks are open to the atmosphere. And tank 1, what we're given is the water surface elevation. WSE is water surface elevation. So the elevation of the water at 1 is 200 meters. And the elevation of the water in tank 2, which is also open to the atmosphere, the water elevation there is 190 meters. Now the pipe, we have the diameter of the pipe, and we are given a special equation that's relating velocity to head loss. Now, you'll notice if you look on the equation sheet that I've given you for the exams, that there's a formula on there that says H sub F equals FLV squared divided by D2G. This is called the Darcy-Weisbach equation. And we'll spend like almost the first 2 weeks of hydraulic engineering talking about this equation. In this example, we're kind of simplifying things a little bit. And so we're saying all of the energy loss in the system, including the local losses and the friction losses. So in this case, all of the energy losses can be accounted for by some factor 0.04 times however long the pipe is times velocity squared divided by 2g. So the 4 has that on it too. What we're saying is that we've wrapped up into this 0.04. That's a friction factor that's related to the roughness of the pipe. It's accounting for the diameter of the pipe, as well as any kind of energy losses due to the bends and the entrance to the pipe, the exit to the pipe, and so on. So I just wanted to tell you this is reality, and this is, for purposes of illustration, the first time you're using the energy equation. All right, so here's the energy equation. What you do is plug in the energy at 1, plug in the energy at 2, and remember 1 and 2 can be any place in the system. You've got water that's flowing from one reservoir to another reservoir through a pipe. And the beautiful thing of the energy equation is it's valid everywhere in the system. So if I wanted to, I could say, here's location 1, and here's location 2, and energy equation is going to work. As long as the water's flowing that way, and it is. Water's flowing downhill. Or I could say, here's location 1, and here's location 2, and then energy equation will be able to do its thing. But we have to be smart about where we pick the locations. And in the past, where we've been sort of smart and strategic, what were we trying to accomplish by being careful with where we picked as location 1 versus location 2? Why were we being so picky about what we used for those points? Stuff to cancel out. So what do you mean? Elaborate. Okay. So yeah, he's remembering that in the energy equation, we've got a lot of terms here. So if I just pick some random spot in the tank, I don't know what the pressure is right there. So I'm going to have to calculate the pressure. Where's an easier place for me to pick as location 1? Yeah, up here. Because, boy, I know a lot of things right at the elevation, at the top of that tank. I know the elevation, I know the pressure, I know the velocity of the water. You know, since it's a big tank, the velocity is 0. So I know a lot of stuff at 1. So I can do the same thing with location 2, picking a smart spot for what is location 2. And so in this equation, the only unknown is going to be v, the velocity of flow. And once you know the velocity of flow, you can find the flow rate, which is what it's asking for, the volumetric flow rate, Q. All right. So I'm going to stop talking and give you a few moments to work on this one. Okay, so the question I just got is, here HL is 0.04 L V squared divided by 2G. The V means velocity. And what it's talking about is the velocity in the pipe, not the velocity at 1 or the velocity at 2. It's talking about the velocity that the water is going through the pipe. So that will end up being your only unknown when you substitute all the rest of the values into the formula. Yeah.
It's just like a problem with my units. So whenever I take the square root, I'm getting my units to be meters over seconds squared. Because whenever I solve this out, like not actually solving for V, I'm getting seconds squared. So I'm getting my head loss to be meters squared instead of meters, and that's what Jacob's getting too. So we're trying to check it.
Well, hold just 1 second. Let me bring this up. All right, so I've gotten a question about the units, and What I should point out is that this Darcy-Weisbach equation, where we have FLV squared divided by D2G, this is an empirical equation, which means that it's generated just based on observations of nature rather than some fundamental understanding of physics. And so F, this friction factor, doesn't have units in the same way that we would think of a normal fundamental equation, because the left side of the head loss formula is going to be meters. The units of head are always in meters. But you don't get meters out of that if you have L times V squared divided by D and multiplied by G. So here in the solution, where I have just canceled out the pressure head term, so where I canceled out the pressure head term and the velocity head term, because we're talking about a tank at the top surface of a tank, and just put in the elevation, and there's no pump between 1 and 2, so that's a 0. And then 0 for the pressure and velocity head term at 2, and then here's the elevation at location 2. There's no turbine between 1 and 2, and then here is the head loss formula that we're given, the empirical head loss formula. So just the fact that it's an empirical formula means that the units aren't going to work out, and you should just be okay with it. Yeah?
Well, if you have that F that's unitless divided by your diameter, shouldn't that be meters inverse? I just don't get it.
Yeah. Yeah, well, hopefully you'll get it next semester. Next semester is when it'll matter more, whether it has units or not. So who got 0.476 cubic meters per second? All right. So let me ask you something. So you found the flow rate for the given situation. Isaac, what would happen if you raised Z1? So let's say that you lifted the tank higher. What's going to happen to the flow rate? That's right. It would make the flow rate higher. He got it, guys. He got there. Well done. No, I'm glad you thought through it. You could have just guessed at random, but I'm glad that you thought through it. You're right. So the phrase I want to introduce is driving force. Like, why was the flow going from 1 towards 2? It's because there was more elevation at 1, meaning it flows from high energy towards low energy. Flow always does that, whether it's just an isolated pipe section that we're thinking about. Like if there is some pipe that continues in both directions, but we measure here at 1 some pressure, and here at 2, if we measured, like P is 100 kPa, and we measured at another point that the pressure is 90 kPa, even without having X-ray vision, I can't see into the pipe, but I still know that the water's going that way, just because water always flows from location of high energy towards low energy. That's why it goes downhill. That's why it flows towards locations of lower pressure, and that even is the same in our atmosphere. You know, wind is basically caused by air movement from high pressure location to low pressure location. And so you may be wondering, well, why would there be places where the pressure is low? And that's because of heating of the air, you know, during the day and during the night. So sections of the earth get heated and cool at different rates. So soil cools at a different rate than rocks. Water cools even more slowly than either of those two. So, you know, changes in pressure cause flow. So what will happen if Z is raised? The flow rate would increase. Let me ask you this. What do you think would happen? Like, what does your instinct tell you the flow rate response would be if we made that pipe, leave the Z's the same, what if we make the pipe a larger diameter? What is that going to do to the flow rate? Decrease. Why would it decrease the flow rate if we make the pipe larger? It would be the same? Q would be the same? Why do you think the flow would go up? Take it to the extreme. Take it to the extreme. You know it's hard to drink a milkshake through a tiny straw, right? Like the little Capri Sun straws. You could never drink a milkshake through that, right? But have you ever had a milkshake with like a big fatty straw before? There's a movie theater down in Texas called the Alamo, and I love that place because they serve like milkshakes and hamburgers during the movie. They like have waiters that come to you. And it was a revelation when I had a milkshake one time, and it was like a big fat straw, so you could actually drink the milkshake with a big fat straw because there's less frictional losses when you have a large diameter. So the same amount of energy makes the fluid move more easily. So here, if you make the straw bigger, the fluid can flow more easily. So you'd increase the velocity, you'd increase the flow rate for the same driving force because we're spending the driving force on head loss. I mean, all of this cancels out to, in the solution, it all cancels out to, here in this equation, the difference in Z is equal to the head loss. And so the elevation difference all goes into head loss, and the head loss is saying there's the length of pipe parameter, there's the velocity parameter, and so if we make the pipe diameter larger, then that would increase the flow. We'll get into a lot more about the driving force as we look at additional examples. So before we move on, any other questions related to this? Yes? Yeah. Good question. So let's say that you're trying to pump water from a water tank and it's going into a mercury tank, right? So a situation like that, it's possible that you could have more pressure here than there. So the flow could go that direction because, you know, this delta H for a really dense fluid could have a higher pressure at the opening of the pipe than this delta H of water.
In this formula, like in this situation, well, you only have C1 minus C2.
Mm-hmm.
How
it would account for that?
Yeah.
Well, it couldn't because you'd have two different fluids, and what you could apply this for is from one fluid to the interface of the other one. In the same way that when we were doing the hydrostatic equation with different types of fluids, we had to do it in steps. Same kind of thing. We could just go from one interface to the next. Okay, so another problem. Water is flowing from 1 to 2 through a horizontal pipe. It doesn't look horizontal, but let's assume that it is because the picture is taken at an angle, something like that. So we've got a horizontal pipe, and we've measured a pressure difference, and I'd like you to use energy equation to find out what's the head loss between the 2 points. So H sub L, solve for H sub L. And just to remind you, 1 square foot is 144 square inches. On the drawing that's there on the screen, I said 1 was the tank and 2 was the other tank. I should have said here is location 1 and here is location 2. So anyway, Any questions about the example? Let's talk about work. So consider an element of fluid that's going through a pipe. The pipe can be changing in diameter, it can be changing in direction, but there's water flowing from one towards two. Now we know from earlier in the semester that if we're just considering what's on the outside of a control volume, there is pressure pushing inward on our element of liquid from both sides. At one, it's pushing from the left towards the right. Here at location 2, there's a pressure pushing to the left. And this element of water is flowing through the pipe. And so the dashed line indicates where it was at time t. And then this solid line indicates a little bit later at time t plus delta t where that same element of fluid is. So what we can do is we can say, well, let's consider the force of the pressure times the area at both the left side and the right side. And if you know that's a force and you consider some incremental distance, delta L, you can calculate the work from that. And so the flow of work, meaning now the time component there, is if you know the pressure of a fluid, the velocity that it's moving, and the cross-sectional area that pressure is acting across. And so at location 2, the work done would be velocity times the pressure times the area, all at 2. And we give that a positive sign, but there's a negative sign at location 1 because of the area sort of pointing towards the left, which is the direction that the pressure is coming from. So the units of workflow are newtons per second, and that's if you have pressure of newtons per square meter, and you are multiplying it by, I'm sorry, no. The units of work, let's do that. Okay. Yeah. Okay, so we've got pressure, which is newtons per meter squared, multiplying that by velocity, which is meters per second. I'm multiplying that by area, which is meters squared. Okay, so we have the meter squared cancels out, so Newton meter per second. And a Newton meter is a joule, so joule per second. Good. A watt. All right, so that's the flow work. And more commonly, what we'll be dealing with in hydraulic engineering is looking at pumps and turbines. And shaft work is when you're considering either the work done on the flow by a pump, which adds energy to the system. That's why it's on the left side of the energy equation that we've seen so far. Or the shaft work that's done by the flow on a turbine. So that's when we're trying to extract energy from the system. And it's on the right-hand side of the energy equation because it's removing the energy that was at 1 as the water flows towards 2. And some of these turbines can be absolutely enormous. If you look at this picture, the scale of it, here's a guy, and here's the impeller blades. And this is at a hydroelectric plant where they're changing out the impellers for generating electricity at a dam. We are going to stop there for today. Have a great Thanksgiving. You already have seen enough that when you get bored and listless over Thanksgiving break and you start missing me on Thursday, a week from today, when, Tuesday off was nice, but Thursday off, it's like too much vacation, start on your homework assignment. And you'll feel like you're back in your favorite class again. All right. Have a good one.